In this lecture, I am going to talk about matched filter, which is an optimum demodulator for digital communication systems. We have very well developed theoretical tools available to study the subject of optimum demodulation. These theoretical tools are studied typically in an advanced courses of the kind which are known by the names of detection and estimation theory. Once you approach the optimum demodulation problem using detection theory, then that approach is called a non-structural approach. Since we don't have sufficient knowledge in detection theory and other stuff, we are not going to take this non-structural approach. So instead of that, what we are going to do is we are going to take the structural approach. Okay, so your matched filter is an example for the structural approach. So again, this matched filter is an optimum demodulator for digital communication systems. In the year 1943, North, this is NORTH, North devised the matched filter for optimum detection of a known signal in additive white noise. A similar result was obtained in 1946 independently by Van Vleck and Middleton, who coined the term matched filter. So these are the brief history about a matched filter. Now the block diagram of the matched filter is given here. So this is your input A times S of t. So let's say the input is kind of this kind of pulse, and this pulse is contaminated by noise. Okay, by noise, and this is how it might become after demodulation like this. Because of the noise, there is light variation like this. So okay, and that's what you are observing, the sum of the signal plus noise. So this is your observed waveform. Observed waveform, and this waveform is given to circuit, or at present we say this is some block. Okay, so given to a block, and after the block we will need the output like this. So it is shown here. Okay, and you do the sampling. I will explain why do we need this kind of pulse or the output of this block, and why do we need to do the sampling, at what time we need to do the sampling, and what the value should be, and what are the factors which affect that sampled value, and all those things, and threshold. And finally you will say yes, there is a signal, and no, there is no signal. That's what we have discussed in detection theory also. We had two hypotheses, H1 and H2. Which one is true, whether hypothesis 1 is true or hypothesis 2 is true. The same thing we are going to do with the help of matched filter. When I say hypothesis 1 is true, that means signal is present. When I say hypothesis 2 is true, then noise is present, signal is absent. Now let us go step by step. In the input I have the pulse S of t. What is S of t? S of t is the basic pulse shape. Basic pulse shape, and A is the scaling factor. So this is given to the transmitter to transmit, and this signal A times S of t, it looks like this. It's a pulse. Let's say for simplicity, let us take it as a pulse, and this pulse is contaminated by noise. Contaminated by noise. Once if it contaminates, then the pulse looks like this. Like this. Okay, so this is what you are going to observe. Okay, so the observed waveform. So let me call the observed waveform by V of t. Let's say received waveform. Received waveform. Now what is V of t from the figure? If you look at V of t is your input signal A times S of t plus the noise N of t. Okay, so this is what you received. After that, see, this is my signal which I am receiving. Now what can I do in this? Because my transmitted signal is affected by, or disturbed by noise. Therefore what shall I do? I need to remove the noise completely and pass the signal without any attenuation. Therefore this is given to a block. Okay, and the output of block should be ideally it should pass the signal A times S of t, pass the signal completely, pass the signal completely without attenuation. Okay, and what about noise? The noise should be completely rejected. Okay. Reject the noise completely. Okay, so therefore the purpose of this block is, once you receive the signal, the very first step what you have to do is you have to pass the signal completely without any attenuation. Attenuation means by this time you know what it means. Okay, and it should reject the noise completely, but this is something that is not going to be impossible to do, but this is the ideal condition. This is impossible. So in such a case, what shall I do? Okay, because these both are mingled each other and we cannot do that. Therefore what I will do is I will do some other operation, integrate, that is low pass filter. In the block you put a integrator, that is integrate is also, this is your V of t, and let's say the output of the block is U of t, and inside the block we have integrator, or I can say low pass filter. Okay, low pass filter is also called integrator. If you put an integrator, the noise term will be integrated out. So the noise term will be as much as possible, it will be eliminated, and it passes only signal to the output. So let us consider two cases here. Case 1. In the case 1, for the time being, let us assume no noise. So then what will happen? Your V of your received signal is going to be A times S of t plus the noise term will be 0. That means your V of t is a simple pulse. And if the simple pulse, if you integrate, then what will happen? Say up to this point the signal is 0, and after that, this after all integration is an area under the pulse, right? So that it is slowly increasing. It reaches the point. So the entire output will be maximum at this point. What is the time now? Let's say the starting point of the pulse is 0 and the ending of your pulse is capital T. And similarly your integrator is building up here from 0 and slowly goes, and it reaches the maximum point at this point at when t equal to capital T. Okay, at the output of the integrator it reaches the maximum value. So what you do is at capital T equal to, small t equal to capital T, you sample the output waveform. Why do we need to do the sampling? That I will tell you in a minute. And after that what happens? Slowly it comes down. Therefore the typical output of this block will be like this. So the block is filter, and whose impulse response is G of t, input is V of t, and output is U of t. The output will be like this. It slowly increases and again comes like this, and at t equal to capital T it reaches the maximum value. Okay, and if it is a pure signal, if it is a pure rectangular signal, then it is slowly linearly increases, and again not like this. 1 minute. If it is a pure rectangle signal, then it goes like this, and again slowly decreases like this. Now let us take the case 2. In case 2, consider noise. In this case what happens? Your V of t is equal to A times S of t plus some amount of noise also. Because of the noise, your pulse is going to be like this. See, it is going to be like this. Therefore when you start to do the integration, there will be small amount of values. So this values again reaches maximum value and again slowly decreases. This is the output of your it increases, it goes like this. So this is the output of integrator. integrator output if you consider the noise. Okay, so you have the block like this, filter, and this is g of t, the impulse responses, and v of t equal to a times s of t plus n of t, and the output is u of t, and this is going to be slowly, it goes like this. It peaks at t equal to capital T, at least t equal to capital T. So this is a typical waveform at the output of the filter. Waveform at the output of filter when you consider the input is contaminated by noise. So what we are doing is we are passing through the filter and take the samples, and this is the sampled value. So we are taking the sample at t equal to capital T, and the sampled value is going to be this one. And generally we will say, let's say t equal to t naught. Let's say this t naught can be anything that we will generalize later on. Okay, so why are we doing, next one can ask, why are we doing this kind of sampling and sampled value, all those things. Before that, let me address, once you do the integration, then what happens, the noise contribution will be minimized. You know why? Because when I say noise like this is a, let us say, typical noise process. If you integrate on over an infinite interval or over a sufficient long interval, the average value, because if you integrate, the average value will leads to 0. Therefore, the best way to eliminate noise would be pass it through an integrator. Therefore, the integrator circuit will remove the noise as much as possible. That is why we are passing the that is why, in order to eliminate the contribution of noise to a certain amount, to a considerable amount, we are passing this contaminated signal to the integrator. So that is the purpose. Contaminated signal is passed through the integrator. Now later on we will see how to derive the impulse response of the filter. For the time being, we are assuming this is a filter. We are not particularly worrying about what is the impulse response of that filter. Okay, that will derive later on. For the time being, intuitively, let us try to understand that the integrator will eliminate the noise contribution as much as possible, and it peaks at the end of the pulse. Okay, so this is a typical operation of your filter. And then why are we doing the sampling? Why do we need to do the sampling? Why do we need to do the sampling? So that is the next question that one should ask. In digital communication system, we don't really look at the complete waveform at the receiver, at the demodulator. Why? In the transmitter part, we are mapping data stream to waveforms, pre-decided waveforms. In the receiver, what we do is received waveforms to data. So in order to get the data, we need to do the sampling. Okay, so that is the purpose we are doing the sampling. So therefore, we will pass it through a filter such that as much of noise as possible is rejected. Okay, and then you do the sampling at a certain point in time, and if you sample it, we should see a large contribution to a signal. See, your integrator eliminates the noise component and to a certain extent, and then do the sampling. Therefore, that sampled value will give the large contribution to a signal, and therefore we sample it at that time. And what time do we need to sample? At t equal to minimum t equal to should be greater than or equal to capital T. Why do we need this capital T? That we'll see now. Suppose, let's say you have a pulse like this. This is 0 and this is t. Suppose you sample at this point, let's say t1. If you sample at this time, at this point, you don't know what will be the peak value. The peak value occurs only at t equal to, at this point only. At this point only peak occurs. Okay, if you look at the operation of the integrator, so therefore you have to wait at least t seconds in order to see the peak value. Okay, so that is why we are doing the sampling at the t equal to capital T seconds. After the sampling, you have the sampled value and then compare the sampled value with the threshold circuit. There is a threshold circuit here, you can see, yeah, threshold circuit, and compare with the pre-decided value, pre-calculated value, and if it is greater than the pre-decided value, then you say it is yes, the signal is present. If it is less than the pre-decided value, then you say no, there is no signal. Okay, signal is absent. Okay, so this is what generally we will do in the matched filter. So, and now typically the point t naught, when I said t is equal to t naught, this t naught is equal to, generally we have taken t capital T, and this value, this point t naught intuitively should be greater than or equal to the duration of the signal. What is this t? It is a duration of the signal. Duration of the, therefore t naught should be greater than or equal to capital T. So that we should remember. T naught should be a point at which you could have seen the seen most of the signal. In fact, you should have observed most of the signal. So ideally t naught should be greater than or equal to 0. So sampling instant. So two things we need to consider: sampling instant t naught should be greater than or equal to capital T. The reason is you wait till up to t, then you could have seen most of the signal part, at almost all the signal part you could have seen. Okay, therefore t naught should be a point by which you could have seen most of the signal, and in fact you should have observed most of the signal part. Therefore ideally they should be, t naught should be greater than or equal to capital D. See the sampling instant. Okay, so you should not try to sample it before the whole signal duration. Okay, one has try to pass through this filter for the whole duration. After that you do the sampling, because it is building up. You're integrating starting from 0 and up to capital T. So you have to wait up to capital T seconds. Therefore the sampling instance should be located beyond t, or at least the smallest value you can choose is the duration itself. So this is your starting point and this is your ending point. So your integrator will keep on waiting 0 0 0. Once you reach this point, and slowly increasing and starts building up, it reaches the maximum value at t. So at this time you try to sample it. So that is why we are sampling at t is equal to t naught, where t naught is equal to capital T. So this is one part, and the next part is, now after you had observed that for a whole pulse duration, you are starting from Z and you keep on observing up to capital T, and you are getting this sampled value. Now what are the factors which will affect this sampled value? I'm sorry, this is not sampling, it's a sampled value. Sampled value. See, if you integrate that out over the pulse duration, at the end of the integration interval, you will probably see a peak building up at the output. So this is a peak building up. Okay, building up at the output of the integrator. After this symbol duration, this 02 is symbol duration. Therefore, that's a right point to sample it and try to make a decision. So that is a basic philosophy of what is called a structure, and that structure is called a linear structure, that we are going to use it here. And then compare this sampled output with a threshold which is somehow pre-calculated, and that produces a decision like yes or no. That means the signal present or absent in that particular interval. Now our concern is to look at this filter G of t. This filter, maybe I'll draw one more time here. You have the filter G of t, and the input is V of t and the output is U of t. When what we'll try to do is we'll try to understand with this kind of input which contains a signal plus noise. Signal plus noise, and what kind of output you are going to get, particularly at some pre-chosen sampling instant. So our pre-chosen sampling instant is t equal to capital T. Now input is not alone signal, but also it contains noise. If this is a case, and what type of output you can expect at the output, that's our question. Suppose if it is pure signal, your output is slowly building up and it reaches a peak point and again comes down. If it is signal plus noise, either you may go very high value and again comes down, or sometimes you go very slowly and reach low value and come down. So both the values can occur. So this is my sampled value. Either you will get a large sampled value. If noise is more than with the signal, then large sampled value. If noise is very low, then low sampled value. I mean, the noise will contaminates the signal and makes it as if there is a noise and a low sampled value. So the sampled value is determined by not only your signal part, but also the noise part. Because ultimately the behavior of this point is going to be depend not really the output waveform, but the nature of the noise itself. Okay, how you are going to suppose somebody will get like this waveform. How the waveform is that is not going to determine the peak value. So the peak value is determined by the nature of the noise. So how much of this value? This value is important for us. The peak value is important, not the waveform. How the waveform is going to be, that is not important for us. For example, there was no noise, then this value will be completely contributed. This value will be completely contributed by signal alone. You have signal something like this. If there is no noise, then the peak value is due to only signal. If no noise. If noise is there, then that will come and disturb the peak value. Okay, so the presence of noise would disturb the value that you would have seen if the signal alone had contributed. So it might decrease it or it might increase it. So in the presence of noise, that's what I already told you. So it might decrease it or it might increase it. This is the increased value and this is the decreased value. Therefore it might increase or decrease. Therefore the noise will perturb the sampled value. And depending on the magnitude of the noise, perturbation may be quite large. So basically what we like to do is design a filter such that the signal contribution becomes as large as possible and the noise contribution should be as small as possible. Okay, but the noise perturbation remains as small as possible. So that's how we choose G of t. So based on this condition, we need to choose G of t. What is G of t? G of t is impulse response. So how do you define impulse response? You design or derive G of t such that maximum contribution from signal, as much as contribution from signal, and as low contribution as possible from noise. So based on these two factors, we are going to define the G of t, the impulse response of the filter. So if you can maximize the signal contribution to noise contribution ratio, then we will have done a good job and we can hope to make a reasonably reliable decision. Therefore, let's look at the nature of the contribution at the output of the filter and filter due to the signal and due to the noise, and that will help us in designing the filter g of t. So our next job is we need to design the filter. So what are the parameters we need to consider, how to design, that we see hereafter now. So till now we have understood that how your filter has to perform and what are the things that we need from the filter. So let's look at the output of the filter whose impulse response is g of t. Therefore output of filter, as I said, the filter should biased for signal and reject the noise as much as possible. So this is my filter, and as I said, input is v of t, output is denoted by u of t, and filter impulse response is denoted by g of t. And now the output is given by, in the time domain, input is convolved with the g of t. This is a convolution operation. I'm sorry, it is not star. Let me write properly. Now, yeah, it is star now. Now this convolution is written by convolution integral. Convolution integral, let's say g of tau times, let me write as a first step, v of t minus tau d tau, and we know v of t equal to g of tau a times s of t minus tau plus n times t minus tau times d tau. This is your u of t. This is the output of the filter. Okay. Now one important point we need to understand here. What is the input of the filter? Input of the filter is v of t is equal to a times s of t plus n of t. What is a times s of t? It is a transmitted pulse. It is the transmitted pulse. And this pulse is a deterministic pulse. Okay, it's a pre-decided pulse, right? So this is a deterministic waveform. Deterministic waveform. Now what about this n of t? N of t is a noise. It is a random process. Now one can ask a question. Random process plus a deterministic waveform, what will it be? Again, it is a random process. So deterministic plus random process, deterministic waveform plus random waveform, which is again a random waveform. Therefore your input is random waveform to the modulator. Random process, let me call it random process. If the input is random process, then output also random process. V of t is the input. Again it is a random process. So u of t is output. This is going to be random process. Once you have the random process, then how do you characterize it? So random process, you cannot describe it mathematically. You cannot write any mathematical equation for random process. So in such a case, what you do, you have a random waveform like this, and this random waveform you sample at a particular time interval, let's say t equal to t1, and you'll get a random variable, let's say n sub t1. You sample at some other time instance, let's say t equal to t2, and you'll get another random variable nt2. If you have a random variable, then that random variable is described by its mean and variance. So next we want to talk about the mean and variance of the random process or the output process. The input is a random process, so obviously the output also a random process. So once you have the random process, then you can do the sampling. Once you do the sampling, then you'll get a random variable, and that random variable is described by mean value and the variance value. So we'll see what are the mean and what are the variance of this output process. So before that, let me introduce some notation. So my output is u of t, and the expected value of u of t is going to be expected value of output is equal to E times U of t, and this let me denote by A times R of t, where A is a scaling factor and R of t is a just notation. Okay, this is just a notation, nothing more that in that, to simplify, to make our life much simpler. Okay, and this is my mean. What about variance? Variance is denoted by sigma square. So I already talked about this variance in one of the lecture, that your noise is n of t has no real part and imaginary part, because we consider that noise is the complex, noise is conveniently represented in complex representation. Therefore you have n sub r of t in phase component plus j times a quadrature component ni of t are real part and imaginary part. Now variance of real part is equal to sigma square, and variance of imaginary part is equal to sigma square, right? So now your u of t is the is integral of what I say is your impulse response g of tau times a times s of t minus tau plus if you substitute n, you will get n r of t minus tau plus j times ni of t minus tau and d tau. If you find the variance, and this guy will give the variance of sigma square and this guy will give the variance of sigma square, therefore I can write variance of u of t which is equal to, what about the variance of this one? It is 0 because it is a deterministic signal, therefore that guy is 0 plus sigma square which is 2 times sigma square. So sigma square is the variance of real part of u of t, and which is the same as, because the real part and the imaginary part both have identical variances, that means identical power spectral density. So in that case the variance of this is variance of imaginary part of u of t. So this is equal to, this is a case. Therefore if u of t has both real and plus imaginary, then variance of u of t equal to 2 sigma square. If u of t is a real process, I cannot say it is a real and imaginary, I can say complex process. When will it be complex process? When the noise is complex, then u of t will also be complex process. If u of t is a real process, real random process, in such a case u of t is going to be the variance of u of t equal to sigma square. That's it. This is the two result that we need to remember. Now at this point let me stop. In the next lecture I will talk about what are the components which are going to give the contribution to variance, and what are the components which are going to give the contribution to the mean, and then we will try to derive the impulse response of the filter. Okay, so at this point let me stop. Thank you very much.